Look up at the night sky on a perfectly clear night, and with good enough eyesight, you could spot Mercury, Venus, Mars, Jupiter, even Saturn. But there is one planet you will never see, no matter how sharp your vision or how dark the sky. Not because it doesn't exist, but because it's so unimaginably far away that it's simply invisible to the naked eye. And here's what makes that strange. It's not some tiny rock drifting at the edge of the solar system. It's a world nearly 4 times the size of Earth, with winds that approach the speed of sound, storms that dwarf entire continents, and moons that may harbor liquid oceans beneath their frozen crusts. We visited it exactly once in all of human history, and we have no confirmed plans to go back. That planet is Neptune. It is the smallest of the ice giants and the farthest planet from the Sun. A place of colossal storms that appear and vanish without warning, near supersonic winds, faint icy rings, and moons that hint at a violent and turbulent past. Of all the planets in our solar system, it is the one we understand the least. So what do we actually know about it? Let's start at the very beginning, with how we found Neptune in the first place. Because unlike every other planet, Neptune was never simply spotted through a telescope. Its discovery is something far more remarkable. Neptune is the only planet in our solar system found through mathematical prediction alone. In 1846, a French astronomer and mathematician named Urbain Jean-Joseph Leverrier was studying the movement of the then-known 7 planets when he noticed something wasn't right about Uranus. Its orbit didn't quite match what Newtonian physics said it should. Rather than dismissing the discrepancy, Leverrier concluded that the only logical explanation was the existence of an 8th planet, one orbiting beyond Uranus and pulling on it gravitationally, bending its path ever so slightly. He ran the calculations and declared that this hidden planet had to exist at a specific, precise location in the night sky. Astronomer Johann Gottfried Galle pointed his telescope at that exact spot and found Neptune within a single hour. It was almost precisely where Leverrier had predicted. A few days later, Neptune's largest moon, Triton, was discovered as well. But from that point on, Neptune became a world of mystery. It sits at the very edge of our solar system, so far out that at certain points in its orbit, it actually lies farther from the Sun than Pluto. Beyond Neptune, there is almost nothing, just scattered icy rocks drifting through the dark. From Neptune's perspective, the Sun appears roughly 1/30th of the size we see it, and the planet receives about 1,000 times less sunlight than Earth does. This extreme distance and dim lighting made Neptune nearly impossible to study from ground-based telescopes for well over a century. To put the scale in perspective, Neptune orbits the Sun at a distance of around 4.5 billion kilometers, 30 times farther from the Sun than we are. A space probe using current technology would take approximately 13 years just to get there. And because of how vast its orbit is, a single Neptunian year, one full trip around the Sun, lasts 165 Earth years. Since the planet was discovered in 1846, we have only ever witnessed a single Neptunian year pass. Getting there by telescope was difficult. Getting there in person was even harder. In fact, only one spacecraft in history has ever visited Neptune, and it only managed to do so by exploiting a rare planetary alignment that occurs once every 175 years. That spacecraft was Voyager 2. It wasn't until 1989 that we truly began to understand what Neptune looked like up close. Voyager 2 had departed Uranus on January 25, 1986, snapping a final farewell image from 1,000,000 kilometers away as it set course for its last destination, Neptune, the final stop on its grand tour of the solar system. After 3 years of travel at 54,000 kilometers per hour, Neptune finally came into view. Voyager 2 passed just 5,000 kilometers above the planet's North Pole, the closest approach of any planetary flyby. And in those few brief hours, it sent back the first detailed images of Neptune we had ever seen. It confirmed the existence of planetary rings and revealed a number of previously unknown moons. What Voyager 2 found was a world of extremes. The average temperature in Neptune's upper atmosphere sits at around -201 degrees Celsius. Its axial tilt is 28 degrees, close to Earth's 23 degrees and Mars's 25, which means Neptune does experience seasons, just like we do. The difference is that each of Neptune's 4 seasons lasts 40 Earth years. Right now, the southern hemisphere is in the middle of its spring. As it receives slightly more sunlight, it warms by about 10 degrees compared to the rest of the planet. That might not sound like much, but it's enough to release frozen methane from the surface into the upper atmosphere, making the southern hemisphere noticeably brighter. Remarkable given that Neptune receives 900 times less sunlight than Earth. Neptune's atmosphere is primarily hydrogen, which makes up around 80% of it. But it's the methane, roughly 19%, that gives the planet its iconic deep blue color. Methane absorbs red wavelengths of light and reflects blue ones back, painting the planet in that vivid, striking hue. And then there are the winds. Voyager 2 recorded equatorial wind speeds of up to 2,160 kilometers per hour, nearly supersonic. Even stranger, most of these winds travel retrograde, blowing in the opposite direction to the planet's rotation. No other planet in the solar system behaves quite like this. When Voyager 2 arrived, Neptune was hosting one of the most dramatic storms ever recorded anywhere in the solar system. A massive, rotating system called the Great Dark Spot, roughly the size of Earth, spinning counterclockwise with internal winds reaching 2,400 kilometers per hour. That remains the highest wind speed ever measured in the solar system. One NASA analyst described watching the data stream as seeing something brand new every single day. Things nobody had ever laid eyes on before, with changes happening faster than anyone had anticipated. Voyager 2 also spotted a smaller companion storm nearby, which shifted from dark to light as the spacecraft approached. While our understanding of Neptune's weather is still limited, much of what we do know came from Hubble, which has observed the planet periodically over the years. When Hubble turned its gaze on Neptune in 1994, astronomers expected to find those same storms still raging. They were gone. Both of them completely vanished. New storms have appeared and faded away ever since, including one spotted in 2015 that is now slowly dissipating. Jupiter's Great Red Spot has been churning for at least 350 years. Neptune's storms come and go within a few years. Why? The leading theory is that Neptune, like Jupiter, has bands of atmosphere moving at different speeds. Where those bands meet, friction could generate vortex storms. But once a storm drifts away from that energy source, it weakens and dies. Hubble is currently the only instrument capable of tracking these changes, because in most wavelengths of light, the storms are nearly invisible. But in ultraviolet, they become clear. Which raises an obvious question. Uranus is nearly identical to Neptune in size and composition. So why doesn't it have the same ferocious weather? Uranus does have fast winds, but they top out at around 900 kilometers per hour, nowhere near Neptune's extremes. Something else has to explain the difference. The answer may be hidden deep inside the planets themselves. You might assume that Neptune, being farther from the Sun, would be the colder of the two, but it isn't. Uranus is actually the coldest planet in the solar system. Neptune radiates significantly more heat from within than it receives from the Sun. Uranus, by contrast, emits almost no internal heat at all. The leading explanation is that a large object, roughly the size of Earth, may have slammed into Uranus billions of years ago, stripping away its primordial internal heat. Neptune, untouched by such a collision, has retained that heat, and astronomers now believe that this internal warmth is a major driver of its extreme weather systems. As for what Neptune is actually made of, its internal structure is thought to be similar to Uranus, with a rocky core surrounded by a deep mantle of water, ammonia, and methane ices in liquid form. At the boundary between the core and the mantle, the pressure is so immense that methane molecules are believed to break apart, and the carbon atoms, squeezed under extraordinary pressure, may crystallize into diamonds. Neptune could, in theory, be raining diamonds in its deep interior. Not diamonds as we typically picture them, but the conditions deep inside Neptune may produce something even stranger. A liquid ocean of carbon with solid diamond icebergs floating on its surface, and diamond crystals raining down through the mantle like hailstones in a storm. This remains a theory, but it's one that recent laboratory experiments have begun to take seriously, as scientists have only recently developed technology capable of recreating the kinds of pressures involved. Near Neptune's core, pressure is estimated to reach around 7 million times that of Earth's atmosphere at sea level. Neptune and Uranus also share something unusual about their magnetic fields. Neptune's magnetic field is tilted 47 degrees relative to its rotational axis, wildly offset compared to most planets. When Voyager 2 first discovered this about Uranus, astronomers assumed it had something to do with Uranus's extreme axial tilt. But then, Voyager 2 found the same thing at Neptune, which has a far more ordinary tilt. That ruled out the simple explanation. The leading theory now is that Neptune's magnetic field isn't generated deep in the core the way Earth's is, but rather in the electrically conducting liquid mantle closer to the surface, or that the mantle itself distorts and deflects the field, pushing it off-axis. Every planet has some degree of magnetic misalignment, but Uranus and Neptune are in a league of their own when it comes to how skewed their magnetospheres are. Neptune does have auroras, though they are nothing like the vivid light shows we see on Earth. They are extremely faint, partly because solar particles are so weakly charged by the time they reach Neptune's orbit, and partly because of the unusual direction of the magnetosphere. Rather than appearing near the poles as they do on Earth, Neptune's auroras form around the planet's mid-latitudes, a consequence of that tilted magnetic field. These are what are known as SAR arcs, a type of aurora that also occurs on Earth, though so faintly here that you'd need scientific instruments to detect them. On a clear night, SAR arcs could be stretching across Earth's entire sky, and you would have no idea. On Neptune, these auroras had remained almost entirely invisible to us, until recently. In March 2025, the James Webb Space Telescope captured something no instrument had ever managed before: direct images of Neptune's mid-latitude auroras, shimmering in near-infrared light across the planet's atmosphere. It was a first. But Webb didn't stop there. At the same time, it detected something unexpected and deeply puzzling. Neptune's upper atmosphere had cooled dramatically since Voyager 2's measurements in 1989, dropping by hundreds of degrees, nearly halving in temperature over just a few decades. What is driving that cooling, and what it means for the processes churning inside the planet, is still an open question. One possible consequence is that the colder temperatures may suppress the very atmospheric emissions that make Neptune's auroras detectable, which could explain why they remained so elusive for so long. Pulling back from the planet itself, we reach Neptune's ring system. For decades, astronomers suspected Neptune had rings, but couldn't confirm it. Voyager 2 settled the question. Neptune does have rings, though they are among the faintest in the solar system. Extremely dark in color, not particularly dense, and sitting billions of kilometers from the Sun where almost no light reaches them. Spotting them against the blackness of space is about as easy as finding a shadow in the dark. What made Neptune's rings especially intriguing was what Voyager 2 found within them: partial ring structures, or ring arcs, incomplete sections of rings rather than uniform bands. This was unusual. Planetary rings are typically spread evenly all the way around. These arcs appeared to be material clumping together within the ring for reasons that still aren't fully understood. There are 5 known rings in total, each named after someone connected to Neptune's discovery or study. The innermost is the Galley ring, very faint and unusually wide at around 2,000 kilometers across. Next is the Leverrier ring, brighter but only about 113 kilometers wide. Connected to it is the Lassell ring, a broad and very faint band stretching 4,000 kilometers. At its edge sits the Arago ring, slightly brighter and less than 100 kilometers wide. Finally, the outermost is the Adams ring, just 35 kilometers wide but one of the brightest of the five. It has a slight inclination and contains those mysterious bright arcs that have remained surprisingly stable since they were first discovered back in 1980. What keeps them from dispersing is still not known. Now, a journey through Neptune's story wouldn't be complete without its moons. Neptune has 14 known moons, all named after water deities from Greek mythology. 7 of these are regular moons, orbiting close to the planet in nearly circular paths, aligned with Neptune's equatorial plane. Beyond them are the irregular moons, following inclined, eccentric, and often retrograde orbits. The first and most extraordinary of these is Triton. Triton is, by almost any measure, one of the most remarkable objects in the solar system. Visually, it's stunning. Intricate surface patterns and a deep burnt orange hue unlike anything else we've seen on a moon. But what makes it truly extraordinary is its orbit. Triton moves clockwise around Neptune, while Neptune itself rotates counterclockwise. It orbits at an angle of 130 degrees to the planet's equatorial plane. In the entire solar system, no other large spherical moon orbits its planet in the wrong direction. Every other major moon follows a prograde orbit, moving in the same direction as its parent planet's rotation. Triton does the opposite. This is not a minor quirk. It is overwhelming evidence that Triton did not form alongside Neptune. It was captured, likely a dwarf planet that once roamed freely through the outer solar system before Neptune's gravity snatched it. And Triton is no small prize. It makes up 99.5% of all the mass currently orbiting Neptune. It is the 7th largest moon in the entire solar system, bigger than Pluto and second only to Earth's moon in terms of size relative to its parent planet. It orbits closer to Neptune than our moon orbits Earth, which means from Neptune's surface, Triton would appear roughly the same size in the sky as our moon appears to us. The connection to Pluto goes deeper than size. When New Horizons flew past Pluto in 2015, the data it sent back suggested that Triton and Pluto share nearly identical compositions, both covered in nitrogen ice mixed with water ice and carbon dioxide, both displaying reddish patches caused by methane reacting with ultraviolet radiation to produce tholins, a tar-like organic compound. The evidence strongly supports the idea that Triton and Pluto share a common origin, both born in the Kuiper Belt. Pluto is often called the king of the Kuiper Belt, the largest object we know of that formed there. But that title arguably belongs to Triton, which is even larger, and which likely ruled that region before Neptune captured it billions of years ago. How exactly that capture happened is still debated. For an object to be captured rather than simply swing past and escape, it needs to lose momentum. The leading theory is that Triton was once part of a binary system, 2 objects orbiting each other, similar to Pluto and its moon Charon. As Neptune's gravity disrupted this pair, the interaction would have flung Triton's companion away, while Triton itself lost enough energy to be pulled into orbit. The 6 other irregular moons found far beyond Triton are almost certainly captured objects too, likely knocked into their strange orbits by gravitational interactions with Triton during its own capture event. Triton's surface tells a fascinating story. Despite being a moon of the outermost planet, it shows very few impact craters, which means its surface is geologically young and constantly being renewed. Voyager 2 spotted ridges, troughs, plateaus, and vast flat ice plains. Like Pluto, parts of its surface are tinged reddish-orange from those tholins. The terrain is remarkably flat. Surface features rarely vary by more than a kilometer in height. Beneath the surface lies a rocky, metallic interior that gives Triton an unusually high density for a moon. The radioactive decay within that rocky core may be generating enough heat to maintain a liquid water ocean beneath the icy crust, similar to what scientists believe exists beneath the surfaces of Europa and Enceladus. And just as on those moons, cryovolcanism appears to be actively reshaping Triton's surface. Liquid water from the interior erupts onto the surface, much like lava on Earth, freezing almost instantly. This constant cycle of eruption and freezing is the primary reason Triton's surface looks so young. It is, in effect, being repaved from below. Scientists have identified what are called planetii, solidified lava lakes, flat frozen plains surrounded by raised walls, the remnants of ancient eruptions. Alongside those solidified lava lakes, Triton's surface also shows calderas, the collapsed depressions at the center of cryovolcanoes, marking where eruptions once broke through. The water that surged up from below likely carried minerals from the subsurface ocean with it, depositing them across the surface. Some scientists believe this process may even be the source of those tholins and organic compounds found on Triton's surface, which raises a striking possibility. If organic compounds exist not just on the surface, but within that underground ocean, then the conditions for life to have formed there may not be out of the question. Triton's surface is also crossed by long, sweeping lines, likely fault systems caused by tectonic stress or the repeated freeze-thaw cycles the Moon undergoes with the seasons. Some of Triton's eruptions, however, don't come from deep within the mantle at all. Voyager 2 spotted a series of dark, fan-shaped deposits on the surface, some stretching up to 150 kilometers, alongside plumes shooting up to 8 kilometers into the sky. These appear to be driven by something closer to the surface, a solid greenhouse effect trapped within Triton's ice. Here's how it works. Triton's surface is covered in a layer of transparent nitrogen ice, sitting on top of darker deposits like tholins. Sunlight passes through the clear ice and is absorbed by the darker material beneath, which heats up and causes the ice directly around it to sublimate, turning from solid to gas without becoming liquid. Pressure builds in that trapped pocket until the surface gives way and a plume erupts, carrying the dark deposits up with it and scattering them across the ice. A very similar mechanism has been observed at the poles of Mars, where carbon dioxide ice sits over darker layers beneath. The fact that this process operates on Triton at all is only possible because of one thing. Triton has an atmosphere. It's a thin one, just 0.014 millibars, roughly equivalent to the pressure 80 kilometers above Earth's surface. But thin doesn't mean inactive. When Voyager 2 passed, Triton's atmosphere was dense enough to support weather up to 8 kilometers above the surface. The images actually show clouds. And looking at where the eruption plumes deposited their material, you can see that all the dark fans point in the same direction, carried by a prevailing wind blowing across that region of the Moon. Since Voyager 2's visit, Triton's atmosphere has grown slightly denser as seasonal warming has evaporated some of the nitrogen ice on the surface. Like Pluto's, it varies with the seasons. And like Pluto's, it carries a faint haze caused by hydrocarbons that haven't yet been broken down into tholins by ultraviolet radiation. Triton is, in every sense, a world unto itself. Cryovolcanically active, atmospherically dynamic, seasonally changing, and potentially harboring a liquid ocean beneath its frozen shell. It behaves less like a moon and more like a dwarf planet that Neptune simply claimed for itself. The rest of Neptune's moons are far less dramatic, though still interesting. The next largest is Proteus, an irregularly shaped object about 400 kilometers across, which is actually larger than Mimas, one of Saturn's spherical moons. The fact that Proteus hasn't settled into a sphere is explained by a violent collision history. Its surface is covered in enormous craters, some 50 to 100 kilometers across, the scars of ancient impacts that deformed its shape permanently. Some of the inner regular moons act as shepherd moons, their gravity helping to constrain the edges of Neptune's rings. The outer irregular moons are almost certainly captured objects, some orbiting prograde and others retrograde. The two outermost moons, Sao and Niso, hold a remarkable distinction. They are the most distant satellites of any planet in the solar system. A single orbit around Neptune takes them 25 years to complete. This is possible because Neptune has an exceptionally large Hill sphere, the region of space within which its gravity dominates over the Sun's. Because Neptune is already so far from the Sun's gravitational influence is comparatively weak in its neighborhood, allowing Neptune to hold gravitational sway over an enormous volume of space. In 2013, Hubble added another moon to the roster, a tiny, irregularly shaped object just 35 kilometers across, now named Hippocamp. What makes Hippocamp particularly interesting isn't its size, but its likely origin. It orbits very close to Proteus and appears to be a fragment broken off from the larger moon by an ancient impact. One of those massive craters on Proteus was probably the source, a collision violent enough to chip off a piece of the moon that then settled into its own orbit nearby. Hippocamp is almost certainly the largest surviving fragment of that event. And then there is one final object worth mentioning. Not a moon, but something Neptune has nonetheless drawn into a precise gravitational relationship with itself. Designated 2020 VN40, this trans-Neptunian object orbits the Sun in an exact 10-to-1 resonance with Neptune. For every 10 orbits Neptune completes, 2020 VN40 completes exactly 1. Given that Neptune's year lasts 165 Earth years, that means 2020 VN40 takes 1,650 years to circle the Sun once. Its orbital plane is highly inclined, and yet that perfect 10-to-1 ratio holds, locked in place by Neptune's gravity across billions of kilometers of space. It is one more reminder of how far Neptune's influence truly reaches, quietly shaping the motion of distant objects at the very edge of the solar system. So there it is. Neptune is one of the most fascinating and least understood worlds in our solar system. Along with Uranus, it sits in a category of its own, visited once, glimpsed rarely, and still full of unanswered questions about its weather, its interior, and its moons. There is no confirmed mission currently planned to return to it. Given the financial pressures facing NASA, none appears likely in the near future. China has proposed a Neptune probe that could potentially launch as early as 2033, but nothing has been confirmed. If it does go ahead, the discoveries waiting there could reshape what we think we know about the outer solar system. Neptune has more story to tell. It always has. It is the farthest planet, the hardest to reach, and in many ways the most mysterious world we know of. And it's out there right now, 4.5 billion kilometers away, spinning quietly in the dark, with its backwards moon and its diamond storms and its impossible winds, waiting for us to come back. If you found this video interesting, there's a link in the description to support the channel on Patreon, where you can watch ad-free, see your name in the credits, and submit questions directly to the team. And for more content like this, check out the playlist linked on screen. See you in the next one.